This lesson is going to look at scientific units and measurement in particular. So this is a section that's in the physics course, but it's common to all areas of science, especially chemistry, but it does have a special home in physics. So three things we're going to look at in this presentation are: we're going to look at SI units, we're going to give examples of those, we're going to look at basic units, and then derived units. While we've looked at SI units before, these differences between basic units and derived units is a bit new. We're also going to look at measurements, how we measure things, different things we can measure, different equipment we'll use to make measurements, and also errors or things that can go wrong while we're taking measurements. And then finally we'll have our homework section with some revision questions to look back over this slideshow. So Ernest Rutherford is a famous physicist, and he said, if your experiment needs statistics, you ought to have done a better experiment. And what this means is that when you do an experiment in physics and science, you should get precise, accurate answers. It shouldn't be something that would tend to happen or this or that. You should be able to figure out exactly what you did and exactly what you can do, and you can make predictions with that. So in his view, experiments in science should give precise values which can be measured and tested. So you can do it over and over again and get the exact same answer, and somebody else somewhere else can do the exact same experiment and they should find the exact same thing. So that's what it means by repeatable and universal. Physics is closely related to maths, and it tries to yield exact results, or at least as accurate as physically possible. In the history of science, especially this guy Rutherford in his area of physics, what happened was people would make predictions, and they'd predict things and look at the maths behind the fact that it should happen. And then you'd have an experimental physicist who'd go away and try and discover this in a lab, and then you could compare the prediction with the findings. And a prediction is no good without the findings. So physics, again, with units that we're going to look at here and measurement, it's nice that you can measure things accurately. So there's a piece of equipment in the physics lab that can measure things as accurately as 0.000000001 meters. So that's a tiny, tiny measurement. But even in the school lab, we can make that extremely small measurement and we can do it accurately. That's us in the lab. Then in physics, one of the more precise measurements that's made is this thing, which can go down as far as 0.3001 kilograms. So we have to be able to make those kind of measurements. In our chemistry course, we looked at things like electrons. So you need to be able to measure these things to see the mass of an electron. Units then. If we are to measure something, we need to measure it in a particular unit. So if you think about height, a lot of people give their height in feet and inches, and then others give their heights in meters and centimeters. If you're measuring a horse, it's measured in hands. If you're measuring a building, it's measured in stories. So if I tell somebody I'm 6'5", they might not know what that means. They might not be able to compare that. If I say I'm 1.95 meters, that might make sense to them. Same thing if somebody says your weight. If you say that you're 84 kilos, if somebody's used to stone, they don't really know what 84 kilos is. It might be heavy, it might not be heavy. They're not used to that unit, so they don't know what it is. So when we take measurements, we need to be able to communicate and tell people what we measured in. So that bit of information, that is our unit. So numbers without units are meaningless. So we should always give our answers and our units. That's one thing students often forget to do. You got to say what your number is as your answer, and also what it's measured in. If you have 80 meters per second, that might be different, well, that is different than 80 kilometers per hour. So it's important you know the number and what you measured it. SI units then are this international standard. So scientists have decided on a system of units, an international standard, so all scientists can measure in the same unit, share their work, and communicate with each other more effectively. This international system of units is known as SI units, or in French, Système International de Unis. So that's Système International, that's the SI, so that's why it's a bit backward. We'd say international system, which would be IS, but this is SI, or the Système International. So when you're looking for precision, units and measurements are very important. If you take the current climate, for example, if doctors and nurses were making measurements and they didn't have the units, or they all use different units, then it would be very difficult for them to share their work. So if you know, and if everybody uses the same unit, then you can compare things very easily. If you're using different systems, you're looking at different numbers, and then everybody would have to be sitting there with their calculator and converting their figures, and they wouldn't be used to them, so it would be making life a lot more difficult. So orange is a measurement. So this is something the book doesn't really look at, but it is an interesting area. So in ancient times, the body ruled when it came to measuring. So the length of a foot, the width of a finger, the distance of a step, they were all accepted as measurements. So they were close enough for the purpose, but they're not particularly constant. They're not consistent. Your foot, my foot would be very, very different. So an inch. So at first, an inch was the width of a man's thumb. In the 14th century, King Edward II of England ruled that 1 inch equals 3 grains of barley placed end to end lengthwise. So this would be a way to make it more standard. But again, 3 grains of barley, that's not the most standard thing. You might have larger and smaller grains of barley. A hand was approximately 5 inches or 5 digits, fingers across. Today a hand is 4 inches and used to measure horses from the ground. So if you're measuring a horse, that's what you do. You have your hands, your fingers across, and you measure them all the way up. Span then. A span was the length of the hand stretched out, which is about 9 inches. So that will be from top to bottom. So all of these things, again, if you're dealing with markets, if you're looking to get those, there's not going to be that much difference between different hands or different feet, so it will be accurate enough. So foot, in ancient times, the foot was around about 11.02381 inches. Today it's 12 inches, so it's the length of the average man's foot. So the word foot comes from foot. Yard then. A yard was originally the length of a man's belt or girdle. Girdle is similar to a belt, as it was called. In the 12th century, King Henry I of England fixed the yard at the distance from his nose to the thumb of his outstretched arm. Today it's 36 inches. So if somebody was getting a yard of wool, that's what they'd do. You'd be able to wrap it around you. That's the length of your belt, and that's how much you'd get. So then again, to standardize it, and it was often the king who would be the first citizen, their measurements then became the standard. A cubit is another old measurement unit. So in ancient Egypt, a cubit was the distance from the elbow to the fingertips. So today that's standardized at about 18 inches. Lick then. A lick was used by the Greeks to measure the distance from the tip of the thumb to the tip of the index finger. So it's like if you make a gun with your hand from the thumb to the tip. Pace, the ancient Roman soldiers marched in paces. They were the length of a double step, so left foot, right foot, about 5 feet. 1,000 paces was a mile. Today a pace is the length of one step, which is about 2.5 to 3 feet. So again, it is how far you'd walk in a step. So all of those were fine, and they do the job that they needed to do. But as things became more precise, and again, as you go for smaller and smaller measurements, you need to have these agreed upon units. So you're not going to be able to make that kind of measurement to 0.00000, that kind of accuracy, if you're using rough measurements. And if people are trying to reproduce those experiments, it's important they use the same thing. So the meter then is one we'll look at a bit more closely. So the French originated the meter in the 1790s as 1/10,000,000th of the distance from the equator to the North Pole along a meridian line through Paris. So if you drew a line from the equator to the North Pole and you went through Paris, you divided it then by 10 million, and that's what they made a meter to be. So it's realistically represented by the distance between 2 marks on an iron bar kept in Paris. So there's an actual physical meter. So this bar, which is kept under lock and key in Paris, that measures out what a meter is. The International Bureau of Weights and Measures, created in 1875, upgraded the bar to one made 90% platinum, 10% iridium alloy. So the reason for that is iron will tend to rust. So this thing, platinum, iridium, that is a lot more stable. You can look into these things further, and they are interesting. Even there are things called leap seconds. So you have your leap year, which you have on the 29th of February, but there's also leap seconds, because as measurements got more precise, people have noticed these kind of differences. Even the kilogram and things like that, there were something like 9 picograms of that went missing between 90 and 1940, and they reckon that went missing because it was mishandled. So a bit of friction or things like that, so that made it decay. So this thing here, the platinum iridium alloy, that's extremely stable, not radioactive, so that should stay pretty much as it is forever and ever and ever. So in the 60s, the meter was redefined as that far. So 1,650,763.73 wavelengths of an orange-red light in a vacuum. That was produced by burning the element krypton. So the reason, well, that's very complicated. The more you get into physics, the more you can see why. But if you take physical distances, well, those things can change. The globe get bigger, it could get smaller. So they're trying to base them now on things which won't change. So the element krypton, that's always going to be the same. So the globe could get bigger, the globe could get smaller, it could get hit by a meteor, it could get changed in drastic ways. But this thing krypton, that element, that is stable, it's not going to change. So you take that many wavelengths and that's now a meter. More recently, in 1984, the Geneva Conference on Weights and Measures had defined the meter as the distance light travels in a vacuum in that tiny bit of time, measured with a cesium-133 atomic clock, which emits pulses of radiation at very rapid regular intervals. So you've gone from the 1790s trying to measure the distance from the equator to the North Pole and dividing it by 10 million, to then basing it upon the wavelength of krypton, and now the length that light travels in a vacuum in that fraction of a second. So that's what a meter is currently. And again, you just think that a conference about this, so everybody's showing up talking about this and trying to decide what they do. So none of the definitions change the length of the meter. So a meter is still a meter, the sticks in the lab are all okay, but a merely allows the length to be duplicated more precisely and things couldn't change like they would in other ones. Now getting into more straightforward, of course, so that stuff I think is kind of interesting, but it's not essential. So some of the basic units and the quantities we measure, we have length, which is L, and that's measured in the meter M. We have time. When you're doing equations, you give it the letter T, but the unit of it is the second S. Mass is again the symbol M, and the SI unit of that is the kilogram kg. Temperature gets a capital T, and that the SI unit is the Kelvin. You can say degree Celsius, that's pretty much okay, but the Kelvin is the better one. Electric current, then, that's an I, not an L. So current is given the letter I for calculations, and it's measured in ampere, which are known as amp for short, which is a capital A. So they're all basic units. Then we have this new thing of derived units. So derived formula are made up from a combination of basic units. A common formula in physics is one for the calculation of speed. So we'll be looking at this in a future chapter, but speed is equal to distance divided by time. So if we look at the units, well, distance is measured in meters. So you can see that there at the top line of the table. Time is measured in seconds. So that's in the second line. So if we have distance measured in meters divided by time measured in seconds, well, the unit for that is m/s. So that's meters divided by seconds. They do the slash there because it's easier to write it in a line with that in the middle rather than write one over the other. Another way you can write it, instead of m-s, is m space s to the -1. So that -1 superscript a bit up at the top, that shows that it's divided. So this, when we're saying it in English, that will be meters per second, and that means in maths meters divided by seconds. And then that second way of writing it, that's just a different way you can do it. So the meters per second is what I typically write, but that's another way you can put it. Other derived units then are kilograms per meter cubed. So that will be kilograms, which will be a mass, divided by meters cubed, which will be a volume. And another one is acceleration. Acceleration will be meters, which will be distance, divided by seconds squared. So that will be seconds times seconds on the bottom. And again, you have the second way to write it. So if we look at the unit for density there, the kilogram per meter cubed, we now know that density equals mass over volume, because we can tell from the units. Likewise, acceleration is equal to distance in meters divided by time squared. So we get the formula from that there. That's something that's in your homework. So many derived units then, they have their own name. So they don't have these combined things like kilogram per meter cubed. They get their own name. So some of those common ones are watt, which is used in power. Tesla, which you won't study in your course, but you might be interested in from the car Tesla or the scientist Tesla. You have ohm, which uses a Greek symbol. That's called the ohm. And we have the joule, which is J. So that symbol there is the omega, which is used for the ohm. So Greek letters used a lot in physics. So making measurements then. So measuring length, we can measure length a number of different ways. So it depends on what length you're trying to measure would decide what piece of equipment you use. If you're using something long, like maybe 2 or 3 meters, you use a measuring tape. Something around about or less than a meter, you'd use a meter stick. Smaller than that, you'd use a ruler. A trundle wheel then is something different. We'll look at it in a couple of slides. An opsometer, calipers, vernier calipers, and digital calipers. We'll look at those as well. So they're new things you need to learn as you go through this. So there's some of your basic things. So you've got a measuring tape. So maybe if you're getting some clothes tailor fitted, you'd use that kind of tape. That's a tailor's tape. You have your thing there, which I think is just a regular ruler. You have your 8-meter long tape, which your builder would use, and then you got a smaller ruler. Meter sticks then will come in there as well. They're just extra long rulers. So there's some of the basic measuring devices you'd know already. Then we have this one here. This is the trundle wheel. So the trundle wheel, that's a handle, and then you have this round thing here. So this starts here and you go around. So every single rotation of the wheel, that's 1 meter. So if you go 1 meter, you'd line this up. You'd have the start at the start. You put that in the road, and then you would let the wheel run around. Then you got this thing over here, which is the digital counter. So every time this goes around 1, it would click up an extra 1, so you wouldn't need to keep count. So this kind of thing would be useful if you were, say, you want to know the length of a river, so you could walk along by the river and you'd be able to tell how far it goes. Same thing if you want to see how far a road is, you could run along that. If you're having a race with your friends, you want to measure out 100 meters, something like a trundle wheel would be very good. You wouldn't want to use a measuring stick or a measuring tape because that would be too awkward and inaccurate. So this trundle wheel would be used for those kind of things. An oppisometer then, so this is a very small piece of equipment. So we'll use this in class at some stage, but this pointer here, that's where you'd start, and you'd use this on a map. So if you wanted to measure, say, the length of a road and you were using a map, or the length of a river on a map, or even you wanted to find the distance around your hand, so if you could lay all of that out, so instead of top to bottom, if you went around your fingers all the way up and around, how long would your hand be around the outside, so getting a perimeter or something like that. How you'd use this is you'd put this wheel back over here to the pointer. Then you would track the wheel along whatever curved line you're trying to measure. And as you roll the wheel along it, it's going to move further and further out. The longer the line, the further it'll move across. But as you can see on this oppisometer, so it's kind of a funny word, oppisometer, there's no thing to measure it on. There's not a digital scale like on the trundle wheel. So what you'd have to do then is you'd have to get a ruler and say, as you run the wheel out to measure the distance, you put this down beside a ruler and run the wheel back. So the further out it runs, then you measure that going back. So you have to use this with a ruler. So again, we'll look at it in future, but it's a good thing to measure a distance on a map, to measure a curved line, like say a river or something, again on a map. Or you could put down your hand and you could use the trundle wheel to run outside your hand, around about the fingers, and then see what the outside of your hand, the perimeter of your hand would be. Calipers then. So this is another piece of equipment. So this is typically used for measuring the width of something. So you see you got this pointer here and you got this pointer here, so you can measure the outside width of something. Then on the other side, because people are good at designing things, you could use these to measure the inside width. So if you had, say, a pipe, you could measure the outside diameter of the pipe with this end, and you can measure the internal or inside diameter of the pipe with this end. But just like with the oppisometer, there's no measuring thing on this. You need to just hold it like that and then put it up against a ruler and use the ruler to see how wide these things are. So that was a bit awkward. So what they did then was they added the ruler. So this is a vernier caliper. So that's a calipers. This is your vernier calipers. So not a very good picture, but along here there is a ruler. So that ruler is attached. So as these jaws move out, so that's jaws for measuring outer dimensions, you can then measure it directly against this ruler. Again, they have these jaws for inside measuring, so again, outside width, inside width. So if you had a ball, this would be a good thing to measure it with because you could figure out how wide the ball is. Then if you're inside like a tube, you could tell how wide that was. You got a screw so that can open and close and stop it from sliding, and you got a little wheel here so you can roll that wheel out with your thumb to get a bit of extra control. So this has a main scale, which is like a ruler, and then it's got something called a vernier scale. That's why it's a vernier calipers, and that allows you to make very accurate measurements. So that's a vernier calipers. Again, we'll use all of these things in future. Third type, because this is actually a little bit tricky of a thing to use. So you got your main scale and your vernier scale. Again, people digitized it. So as this goes out, the width would change. Here, you can see the 20 there. So that's just a little bit, I guess, before 20 of 19.4 millimeters. So you got your on and off switch. You got your 0, so you can bring that back to 0. And then you can change your units here, so you have millimeters or inches, so you can measure in either depending on which one you're looking for. So they're all different ways to measure things. You got your calipers, your vernier calipers, and digital calipers, all used to measure diameters and widths. So something like your thumb, that would be something you can measure with. Like I said, how wide is a golf ball? That would be another thing, a tube or a pipe. all of those things will be fine for your calipers. You have your opposometer then for maps, and your trundle wheel for outside big distances, roads or fields or things like that. Measuring mass then, so changing your quantity. So what we call weight in daily life, we should really call mass. So when we say what's your weight, what we really mean is what's your mass. Weight is a force, while mass is a measurement of how much matter something has. A 10-kilogram object can be weightless. It can be floating around in outer space, but it can never have zero mass. A 10-kilogram object will always be 10 kilograms. When it floats, that means it's weightless. So mass and weight are different things in physics. So weight versus mass is a common source of confusion in science. There are other examples of things we mix up, but people are happier to leave it as it is rather than change it. So why do we keep making the same mistake? Well, the reason is just because we've always made it. So what I said as another example from more daily life, this is a lot of the keys in a keyboard. It will be easier for people to learn the keys if they were placed alphabetically. But once you know where they are here, so you know Q, W, E, or T, Y, they're the first 6 keys. Once you know that and you can type with these, it's going to be more difficult to retrain people if you did bring in the alphabetical keyboard. So sometimes people are just happier to keep going with how it is rather than changes. This is an important slide, so you need to know 3 differences between mass and weight. So an easy one is mass is measured in kilograms, whereas weight is measured in newtons. Then you have your definitions. The mass is essentially how much stuff is in an object, so how much matter is in there, while weight is a force, and weight is a force that's due to gravity. And a third difference then is mass is fixed, it's a constant, while weight is not fixed and depends on location. If you go up to the top of a mountain, you're slightly less weight than you are at the bottom of the mountain. And not even you can count your sweat, but if you carried a block, whatever mass that was in kilograms at the bottom, that would be the same number of kilograms at the top. Whereas whatever its weight is at the bottom, which depends on gravity, as you go up, you get slightly less gravity, so it would have a slightly smaller weight. So there are 3 differences between those, and again, that's a homework question. So measuring mass, then confusingly, mass can be measured with a weighing scale. So we call it a weighing scale even though it measures mass. An electronic mass balance, or an electronic balance for short, a spring balance, scales, all of those things measured mass. And usually on, especially modern scales, there's a button so you can switch around your units. You can use grams if you're in Europe, you can use ounces if you're in the US, and you can often also get it to measure in Newton, which measures the force directly. Here are some different scales. So you got your platform scales, a bench scales, a digital scales, something like this, a floor scales that will be used in factory. So you got your forklift there. They also use it in dumps. So if you're bringing in a trailer of stuff to dump, what you do is you drive onto it with your trailer. They take the mass of your car plus trailer plus rubbish. Then they get your mass again when you're on the way out. So let's say you weighed 500 kilograms going in. You weigh 450 kilograms coming out. That means you had 50 kilograms of rubbish. So they use something like that to weigh it. The same thing for animals. You wouldn't get an animal to maybe stand in a scale like that easy. So they can put an animal standing on that, and you'll find out how much they weigh then in kilograms. So that's their mass. Measuring volume now. Any of the following can be used, but some are more accurate than others. So they're listed from worst to best. So the beaker is the worst for measuring volume. Graduated cylinder is better. A volumetric flask is better again. A burette, again, a bit arguably is better than that. And then a pipette is probably the best. So a couple of these things you'll use. Some of them you won't use for a long while, but we'll throw them in here while we're at it. When you're revising in 3rd year for your junior certs, you'll know about them then. So here's you got your typical beaker. So along the sides you got 50, 100, 150, 200, and 250. So this will only give you a rough measurement. And again, I'm going to leave you think about this for homework about why this will be a lot rougher than the next one. So keep an eye on the different things and see what maybe makes them more precise and a better measurer. So your beaker is just like a glass, and then they add a little spout for pouring. And you can see here it says approx, so this is only a rough measurement. So beaker will never give you an accurate thing. So if you want to be accurate, you can't use a beaker. A graduated cylinder, then you use those. So these have more measurements. So you can get 5, 10, 15, 20, 25, and you get all the different lines in between. So that's a more precise measurement. And again, you use the graduated cylinder for the right size for what you're measuring. This one measures up to 25 mils, so that will be perfect for anything up to or less than 25. a volumetric flask, then this will just give you one particular measurement. So this volumetric flask holds exactly 100 mils. This is just given a red liquid so you can see it. Along the neck of the bottle, which is harder to make out, there is a line, and that line shows exactly where you need to, yes, it's actually just there. That line shows you exactly where you need to fill this up to have exactly 100 mils, and that's a very accurate measurement of 100 mils. The burette then, so you got this long narrow tube and there's a tap on the bottom. This is used if you want to add a liquid into something. So this will keep track of how much liquid has been added. You'd start off with 0 added, then you'd open the tap down here and you'd let the liquid run out, and whenever it runs out you can close it, and then you can make an accurate measurement of how much you have. So this is again an accurate way to do it. And then a pipette. So again, this is used if you want to measure a precise volume. So this one will measure 100, 50, 25, 10, and then 5. So you got a very narrow tube at the bottom, you got a wider bit, and then you have a long narrow neck. And along the neck there will be a little line, and that would show you where you need to fill it to get exactly this much liquid. So a pipette will only measure one thing, so it's just designed to measure, in this case, 100 mils, and that's a very precise way to measure a volume. The meniscus then is something we need to look at. So when some liquids rest, they do not lie flat. Water, for example, sits in a U shape. This U shape is known as a meniscus. So that meniscus is a key word. So here you can see the meniscus. See, it's slightly higher, then it comes down and it comes back up. So that's what we call the U shape. So the top and the bottom are at different places. So meniscus and measurement. This leads to a problem. In the slide before, you can see that the top of the water is at 37. So if you measure from the top of the meniscus, the top of that U, it's up here, the top of the U is at 37. Whereas if you measure from the bottom of the meniscus, it's at 36 centimeters. So that's your 30. So see, that's 30. The long line is for 5, that's up to 40, so that's 35 plus 1, that's 36. So the bottom of the meniscus is sitting there, while the top of the meniscus, it's creeping up the side, and that top of the meniscus, that's up an extra centimeter cube, that's up to 37. So again, like we said, we need the standard unit, so we need a precise way to measure that we can all agree on. Because if some people use the top of the meniscus and some use the bottom of the meniscus, that's not going to give us good measurements and they're not going to be reproducible. So for this reason, it was agreed that all measurements be taken from the bottom of the meniscus. So when you're taking a measurement, you always measure from the bottom of the meniscus. And that is the better way to do it because this is more accurate. Water, it gives that U shape because water tends to climb up the glass. So the lower point is more accurate. That's the lower point is where it is, and then the side is where it climbed up to. Water has a larger U and narrower containers. So the middle at the bottom is the most accurate. So if you have that middle at the bottom, that's going to move the least. If you have a very wide container, you'll have a smaller U, so the top of the meniscus will be lower down. Whereas if you have a very narrow container, then the U will climb up higher. So for clear liquids, the bottom of the meniscus is the easiest point to identify because you can see through them and you know exactly where that is. So for accurate measurements, all readings should be taken at eye level. So you need to look at it exactly from the side. So when you take your reading and you know off by heart by the end of your chemistry course, you take all readings from the bottom of the meniscus at eye level. It's very important if you want to be accurate. So mercury is another liquid that has a meniscus, but it's a different meniscus. This forms the inverse, the other way around, and it gives an N shape. So in mercury, readings are taken from the top of the meniscus. So in both cases, the readings are always taken from the center of the meniscus. So that's an easy way to do it. So here you have your two different meniscus. So your water gives this U shape. So it's a little bit higher at the sides than it is in the middle. And then in mercury, that goes up. So that's an N shape. So the reason that is the particles tend to pull together and you give this drop effect. So a fancy word for physics is convex. Convex is anything that's pushed up. Concave over here, so this kind of caves in. So that's your concave meniscus and your convex meniscus. So you always read from the middle of the meniscus. So you're the bottom of the meniscus for water, and if you have a barometer which uses mercury, you'd read it from the top of the meniscus. Now, the last section we're going to look at is different kinds of errors. So the first error you can have when making a measurement is a random error. So as the name suggests, random errors occur randomly. They happen when you do your best to take a reading, but something just goes wrong. So you did it properly, but just you didn't get a good reading. For example, you might stop or start a clock too slowly, A piece of equipment might move, the environment could change, so you might be measuring the temperature of water and the room might get a bit sunnier, and then that could be get that bit of extra heat. So that will just give you a random error. Random errors will be single figures that are different to other ones you took. So a random error will be different. So you do it a few times and there's kind of a figure it should be at, but you had just a reading that was a little bit off. So that would be off due to a random error. So some random errors cause results to be too high, other cause it to be too low. And for that reason, it's always a good idea to take a number of readings and then you get the average. So you're not going to be able to do something precisely. But if you do it 4 or 5 times, some might be a little bit high, some might be a little bit low, and the true answer will be in the middle. Here's an example of something called parallax error. So it says a matter of perspective. So if you look at this photograph here, I look like I'm less than 31. So what this is 31 feet. This is beside a river here, so they measure the height of the river when it floods. So this would be 31 feet above sea level. But if you look over here, well, that one kind of looks like I'm 34. So it didn't grow that much. So parallax error is something you can get if you're looking down or if you're looking up. So like we said with the meniscus, the best way to take a measurement and the best way to take any measurement is always to look at eye level. My true value will be somewhere between the two. Because that's a downward angle, it makes me look like I'm less than 31. But if I brought that camera down level with my head, then I'll be over 31. Here again, if you look at the peak of the cap, it looks like I'm over 34. If you look at the top of the cap, it would be more like 33.5. So that's kind of where my head would be. So if you have the same person, the same measurement at different angles, that gives you then a parallax error. So that parallax error could be a little bit random, because if you try to be eye level, you might be a little bit higher or lower, so that could be a random error. But it could also fall into the different category depending on if you kind of knew what you were doing. But parallax error is an important error, and anytime you make a measurement, unless it's digital, you can get a parallax error. So systematic errors, so we had random errors, now we got systematic errors. So these occur when there's an error in your system. That means how you're doing it. So you were doing it wrong. So for a systematic error, you can get the wrong value exact, like the same exact wrong value. So you might be supposed to measure 32, but you're measuring 31, 31, 31, 31, 31, because the way you're doing it, your system, you're making a systematic error. You're making the same mistake every time. So you could be measuring from the wrong point. You could be misusing a piece of equipment. Like sometimes people might use a ruler, and what they might do is they might have centimeters on the top and bottom. But on the top it might go from 0 to 30, and on the bottom it might go from 30 to 0. So they could be looking at the wrong side of the ruler. So that could give them a systematic error. A zero error is a common systematic error. This happens when your piece of equipment did not start at 0. So that's what we call a zero error. So it didn't start at 0, so it won't have gone the correct distance. Parallax errors occur when you do not take measurements in straight lines at eye level. So parallax errors occurs for all readings unless you have a digital output. If you got a digital output, it doesn't matter on your angle. Now, this is a ruler. So this shows 30 centimeters or 12 inches. And 12 inches is what we take to be a foot. So the question is that ruler exactly 1 foot long? And you look and you check and you double check. It starts at 0, goes up to 12. So yes, that would be a foot. However, you see there's an extra bit here at the start and there's an extra bit here at the end. So because of those extra bits, it's not actually starting at 0. So if you put this ruler down and you measure from the start of the ruler to the end of the ruler, you'd actually have a little bit more than a foot. So that is what we would call a zero error. So you're not actually starting at 0. Likewise, if you have a ruler that does start at 0 but it's old, some of the end can get worn away. So maybe some of it just got frictioned off, it eroded from too much rubbing, so it might be a couple of mils shorter. So then you have another type of zero error, so it's actually starting a little bit after 0. So all of this might have worn away and you might be starting from about here. So you're not starting at 0 again, and then that's a problem. So this is the start of your homework question. So first off is go back to the slide and learn the SI units. That's an important thing, and you'll be asked those in tests on physics. So then, using your knowledge of units, measurements and formula, complete the following. So this is meters per second, and what this is in maths, this is meters divided by seconds. So when it's meters divided by seconds, For this one here, this one is distance, because meters is a measure of distance. So this is distance, then the line means divided by, then we have S. S is seconds, which is time. So this one is distance divided by time. Now if you want to try the rest of them, pause this so I don't give you the answers, but if you probably find this tricky, so if you want to listen, I'll give the answers to them here. So this one here is kilograms. So kilograms is a unit of mass. So that's mass, again, divided by, then we have meters cubed, so that will be volume. So that's meters divided by volume. Here we have M, that's a capital M, but that was an autocorrect, so that shouldn't be there. That should be a small m, so just give me a second. So that is meters divided by seconds per second squared. So this is meters, so that's distance. Again, that's a -2. So because it's a -2, that means divide, and that's divided by time squared. So that's distance divided by time squared. This one here, J, that's your unit of joules, so that's from your energy. So it's energy, and again that -1 divided by K for Kelvin, which is temperature. So that's energy divided by temperature. And this last one here, N, is for Newton, which is a unit of force. So Newton, and see there's no line here or minuses, that's newtons, which is force, multiplied by meters, which is distance. So that's force multiplied by distance. So if you ever see a unit, you should be able to figure out what the thing is and how you get it. So if they give you the unit for your answer, you can figure out the formula from that. Then this is the last slide. A unit has been produced from combining basic units, is known as watt. So it's not a basic unit, it's the other kind. What can you use to measure accurate widths or thicknesses? So this was given in the slide here. It's not a ruler, but there are other things in the slide that you could use. There's 3 different types, you can pick any one. Give 2 differences between mass and weight. There's a slide which shows 3, so pick out and learn 2. Look at the different ways to measure volume from slides 21 to 26. Why do you think some are more accurate than others? So look at your beaker, look at your conical flask, look at your volumetric flasks, your burettes and your pipettes. What makes the pipette accurate? What makes the beaker inaccurate? Next question, what type of error is caused when there is a difference in the reaction times of 2 people? So if 2 people just happen to start it or stop it differently, what kind of error would that be? What type of error then will cause all readings to be above or below the true value? So what would consistently give somebody the wrong answer? What kind of error? And then the last question, what piece or pieces of equipment will be most suitable to find the length of a road? So that's very long, so it's going to be too long for your measuring tape. So what could you use? And then next one, what about a road on a map? So a curvy, bendy road on a map. What piece of or pieces of equipment would you need to take those measurements? So give those a go. You can write them out and photograph them, or just type them up in Word and attach the Word document then. So best of luck.